What we're going to do is start with an intermolecular forces summary. There are three types of intermolecular forces, which we will shorten to IMFs, also known as van der Waals forces, that brings molecules together. There are dipole-dipole interactions, hydrogen bonding, and London dispersion forces, often shortened LDFs. There is a fourth intermolecular force between ions and molecules. Those are called ion-dipole interactions, and they're not considered a van der Waals force. This only mainly occurs in solution phases where you have molecules of a solution and ions. All right, let's talk about how intermolecular forces affect boiling points. The kinetic energy of the molecules is proportional to the temperature. So as the kinetic energy rises, or as we increase the temperature of a solution or a bunch of molecules, so does the kinetic energy. The boiling point of that solution refers to the temperature at which the molecule's energy overcomes the intermolecular forces keeping them together attracted. The higher the boiling point of a substance, therefore, the stronger the intermolecular forces. Water molecules, as an example, overcome their intermolecular forces at 100 degrees Celsius. Let's spend some time talking about the intermolecular force known as dipole-dipole interactions. Molecules that have permanent dipoles are attracted to each other. The positive end of one is attracted to the negative end of the other, and vice versa. These forces are only important when the molecules are close to each other. Only polar molecules will have this type of intermolecular force. The more polar the molecule, the stronger the attraction between the molecules, the higher the boiling point, and the higher the melting point. So here I have a polar molecule, a neighboring polar molecule, a neighboring polar molecule, a neighboring polar molecule. So we can see the interaction between any two like polar ends is in this dashed line in black. The interaction between any two opposite charged polar ends or oppositely polar ends is in red, and that allows us to see that dipole-dipole interaction. All right, let's talk now about hydrogen bonding. Hydrogen bonding is a form of dipole-dipole interactions, but specifically they're the dipole-dipole interactions experienced when a hydrogen atom is bonded to either nitrogen, oxygen, or fluorine. These types of interactions are unusually strong, and we call them hydrogen bonds. Hydrogen bonding arises in part from the high electronegativity and small radius of a nitrogen, oxygen, or fluorine atom. When hydrogen is bonded to one of these very electronegative elements, as we see in this water molecule, the positive hydrogen nucleus is exposed. So we have a very, very highly partially positive here and a partial negative here. And that creates this very strong dipole and this very strong hydrogen bond between the molecules. All right, let's finally talk about London dispersion forces. London dispersion forces occur between all molecules. So all molecules exhibit London dispersion forces. They result from the fact that electrons are in constant motion and sometimes are on the same side of the molecule. When the electrons are on one side, the molecule itself is polarized. One side is negative, as you can see down here, and the other is positive. This is an instantaneous dipole. Of course, as soon as the electron continues to move, it goes away. The polarization here creates an electric field that oppositely polarizes nearby molecules. So this positive here will draw the electrons from a neighboring molecule toward it. And we get an induced dipole results, leading to an attraction between these nearby molecules. All right, let's talk about polarizability as it relates to these forces. London dispersion forces are present in all molecules, whether polar or nonpolar. The tendency of an electron cloud to distort in this way, where you have this instantaneous dipole within an individual molecule, is called polarizability. Because larger molecules have more electrons, they are more polarizable. Molecules with more electrons, therefore, experience stronger London dispersion forces. The greater the number of electrons, the more polarizable the particles are, resulting in stronger London dispersion forces. All right, let's compare and contrast those dipole-dipole interactions with London dispersion forces. London dispersion forces. If one molecule is much larger than another, dispersion forces will likely determine its physical properties. If molecules are nonpolar, dispersion forces will dominate since all molecules experience those dispersion forces. However, if two polar molecules are of comparable size, the dipole-dipole interactions will be the dominating force. There is a fourth intermolecular force that exists between ions and molecules that will be important as we explore solutions later. Ion-dipole interactions are that fourth intermolecular force, but they are not considered a van der Waals force. The ion-dipole forces cause ionic substances to dissolve in polar solvents. So, if you put your sodium chloride, NaCl, into water, that ion-dipole attraction, so the attraction of the oxygen end of the water to the sodium ion and the hydrogen end of the water to the chlorine ion, is what pulls those ions apart, allowing them to be solvated and for that solid to dissolve. All right, so here's a summary of intermolecular forces. So first of all, are ions involved? If the answer is yes, are there polar molecules and ions both present? If not, then it's just an ionic bond, okay? And it's the electrostatic force holding those ions together. If you have polar molecules and ions both present, then we have ion-dipole forces, similar to what I described in the previous slide about sodium chloride in water. Okay? Now, what if there are no ions? First, are polar molecules involved? If not, then you only have dispersion forces. Okay? If yes, look for hydrogen bonding. So hydrogen bonded to NO or F. If no, you only have dipole-dipole forces. If yes, you have hydrogen bonding. These three are van der Waals forces. These two involving ions are not van der Waals forces. Here's a summary of intermolecular forces comparing molecules of similar mass. Okay, so if three molecules or two molecules have a similar mass, how would we describe the intermolecular forces? So if they all have comparable mass, then the dispersion forces would be the weakest and the hydrogen bonding would be the strongest. All molecules, both polar and nonpolar, would have dispersion forces. Only polar molecules would be dipole-dipole. And of course, if I had hydrogen bonded to nitrogen, oxygen, or fluorine, would have hydrogen bonding. When in doubt, look at the number of electrons when determining the strength of dispersion forces. Look at the dipole moment to determine the strength of dipole-dipole. And for hydrogen bonding, look for these specific bonds. All right, let's talk about how these intermolecular forces affect the properties of liquids. We'll start with viscosity. Viscosity is the resistance of a liquid to flow. It's related to the ease with which molecules can move past each other. Viscosity increases with stronger intermolecular forces. So that means the stronger the intermolecular forces, the more a liquid resists flowing, and decreases with higher temperature. Surface tension results from the greater attraction of liquid molecules to each other than to the molecules in the air. The net effect of surface tension is an inward force at the surface of the liquid that causes the liquid to behave as if its surface were covered with a stretched elastic membrane. The surface tension of a liquid is directly related to the attractive forces between the molecules. The stronger the attractive forces, the more surface tension is needed to increase the surface area of the liquid. One more property of liquids that's affected by the strength of intermolecular forces is volatility. Volatility is a measure of how readily a substance vaporizes or transitions from a liquid to a gas phase. The more volatile a liquid, the more quickly it evaporates, the higher its vapor pressure at a given temperature, and the weaker its intermolecular forces. It would make sense that if the forces are weak, the substance would more readily go from a liquid to a gas. Okay, so another characteristic of a liquid based upon the strength of intermolecular forces is this volatility. Boiling and evaporation are two ways in which a liquid can vaporize into a gas. However, there are important distinctions between these processes. Evaporation occurs below the boiling point and occurs only at the surface of the liquid, where it evaporates from liquid to gas. Boiling occurs at a specific temperature, the boiling point, and it occurs throughout the entire liquid. It is achieved when the atmospheric pressure, or the pressure of the atmosphere, equals the vapor pressure. What is this vapor pressure? Well, vapor pressure is the pressure exerted by the gas molecules above the surface of an enclosed liquid. So you can see in the diagram here, we have two temperatures, T1 and T2. T1 is lower, so we're increasing the temperature here, okay? The blue are the liquid molecules at the surface, and the gray are the vapor molecules, okay? So sample A at a lower temperature shows some vapor above the surface of the liquid. Sample B at a higher temperature shows a greater number of vapor particles. Well, so if there's more particles escaping to that vapor phase, there's more there to exert a higher pressure, okay? So as the temperature increases, the number of vapor particles increases, the vapor pressure also increases. And as we just discussed on the previous slide, once that vapor pressure increases to be equal to the pressure of the atmosphere, that is when boiling occurs. Shown in the diagram is a vapor pressure curve where you have vapor pressure on the y-axis here is being measured in torr, or millimeters of mercury. And here you have temperature in Celsius, okay? The boiling point of a liquid is the temperature at which its vapor pressure equals atmospheric pressure. So see this line here, 760? That's atmospheric pressure, okay? So when the vapor pressure gets to that point, this would be the boiling point. So as the vapor pressure increases to that 760, that would be the boiling point. So each point along the curve shows the temperature at which atmospheric pressure equals vapor pressure, or the boiling point for a given vapor pressure. The normal boiling point is the temperature at which its vapor pressure is 760 torr, or that standard atmospheric pressure of 1 atmosphere. One final detail on boiling point as it relates to atmospheric pressure. Remember that boiling occurs when the vapor pressure equals atmospheric pressure, but atmospheric pressure varies with altitude, right? How much the atmosphere is pushing down at a given location. Remember, maybe you don't, but maybe if you remember from some physics background or some previous chemistry, we can draw a column of air up representing the atmosphere, and obviously if that column gets smaller as the altitude increases, then the vapor pressure also then will decrease. So atmospheric pressure is much lower at high altitudes. As we see here, the difference at sea level in New Jersey, let's say 101.3 kilopascals versus on Mount Everest 33 kilopascals. So that means that vapor pressure will equal atmospheric pressure at a much lower temperature. Okay, so water will boil at a much lower temperature on Mount Everest than it will in New Jersey, right? So this is why things like baking temperatures and other things change with altitude, because that atmospheric pressure really does affect things.